So, good afternoon, everyone. Uh, my name is Konsta Sipilä, and I've been working at VTT for past 10 years now. My background is in material sciences, and in Finland, I've been working in national projects related to polymers in nuclear. And these topics are rather interesting because you can kind of get familiar yourself with different research area. You probably have seen that aging is closely related to chemistry, and then we have these different kind of research methods that are used to detect aging. So this kind of cross field, different technologies and sciences. This is a really interesting topic for me. And today, my presentation is about mechanical testing used in the aging evaluation of cables. So first, I have a brief introduction to VTT. So VTT is the Finnish Technological Research Center. It's government-owned facility, and it was established in 1942. And it is actually the very root cause established VTT was related to the Second World War, and when the artillery barrels used in the war ruptured in the very cold winter time. So the government decided to establish this materials research center to find the cause behind these ruptures. So VTT started kind of a material science institute, and during the past decades, it has started also or widened it to other research topics such as nuclear industry, electronics, and also biorefineries. We are not perhaps that much focused in basic research. We are more like applied research. We do it together with our partners in industry and universities. Currently, we are about 2,100 personnel, and about 150 persons on this amount is currently working with nuclear-related topics. So, this presentation, how to use mechanical testing evaluate the aging of cables. So, in this presentation, I will briefly introduce different methods that we use in measurement of cable mechanical properties. These measurement techniques include tensile testing, hardness testing, ultrasonic testing, and dynamic mechanical analysis. And for tomorrow, we have another presentation coming from VTT, and in this tomorrow's presentation, the focus is on modeling the mechanical properties as a function of aging. And tomorrow here we'll be speaking Jukka Vaari and Vyacheslav Balabanov, and they will give you a brief introduction in molecular dynamic simulations and finite element simulations in aging modeling of polymers. So briefly about backgrounds, you probably have heard this already in previous presentations. So the main function of cables used in nuclear power plants, they need to transport electricity and signals to different kind of control instrumentations. This is a common estimate that there is roughly 1,000 to 2,000 kilometers different types of cables used in various locations and instrumentations in nuclear power plants. Typical instrumentations include motors and actuators for power operated valves. Obviously, it is beneficial for the plant owners that the cables are maintained in good condition. So the most important aims of this kind of type of research is to ensure that the cables are in good condition during normal operation conditions. In addition, some of the equipment or instrumentation have some safety relevance, meaning that they are used during accidental scenarios. So that's why cabling of these equipment needs to be in good condition as well. And a wider challenge facing the whole nuclear fleet in Europe and US is that most of the nuclear power stations, they were built during 70s or 80s. So they are closing or even surpassed their originally designed lifetime. And as for any other component, when we extend the lifetime of these nuclear power plants, we need to ensure that these cables will be in good condition for the planned extended lifetimes. So there's a clear need for cable condition monitoring strategies that we need to define the good cable or ensure the good cable condition. So this is more like a philosophical slide asking what is aging, and in this sense or in this context, aging can be defined as degradation of material properties that ultimately lead into cable not being able to function properly. And what this could mean in the mechanical point of view and macroscopic point of view. So basically, it would mean that the material, it would lose its ductility and strength. Actually, I have I'm not sure how well you can see, but I have this small, neat XLPE tape. And as you can see, it's in good condition. You can bend it, it has strength. I cannot break it. And then on the other hand, I have also an example of aged material which has lost its ductility. It's here. And this material is fragile. You can break it into pieces. So concrete example what the aging is in mechanical point of view. So one essential part of measuring the cable good condition, whether it's mechanical or other property, you should have a proper acceptance criteria, at which point the properties are still sufficient and will show you that the cable is still in good condition. And this acceptance criteria, this should be based on that the cable you should be able to handle it in normal way, and it also should endure all the vibrations that it will face during normal operations. So that would be a good starting point when setting an acceptance criteria for in the mechanical point of view for cables. And then the second philosophical question in this slide is why cables age. I think it was really good presentation from this morning from Karel. He went quite detailed through different environmental factors which would affect the cable aging. But here I have listed three most common ones inside nuclear facilities. There are temperature, radiation, and moisture. And of which just three, the temperature withstands to be the most important one during normal operation. Of course, during the accidental operations, you have high doses of radiation as well. So then we move on, going through the different mechanical tests. And the first one, we have a tensile test. So basically, tensile tests can be defined to be measurement of the ability of the material to overcome forces, pulling the sample apart, and the extent it stretches before breaking. So basically, this means how much your sample can withstand force without breaking, and how much it can stretch without breaking. This is a destructive method, obviously, and quite old one also, and that's why it has been quite well standardized. And most of the tensile test standards based on ISO and IEC standards, and typically these standards they have or they include something about the terminology generally used in tensile testing, description of the used apparatus, information or instructions on the sample geometry, shape, gauge length, for example. Then describing the actual procedure, how to perform the tensile test. Here, for example, it should include the test speed, how fast you would pull the test, and then of course the treatment of the results. Here on the right hand side, you can actually see a figure on a tensile test. So the tensile test equipment, you clamp the sample between these crossheads, And usually one of these crossheads is rigid, it doesn't move, and the other one moves in axial direction. So based on this movement of in these axial directions, you can define the engineering strain for the tested material. So it's basically the original gauge length divided by the change in the length during the experiments. Similarly, you can define when you have a simultaneous measurement of force applied on the sample. You can calculate then the engineering stress, which is the applied force divided with the cross-sectional area of our sample in the initial state. So here you have a single tensile test or screenshots from a single tensile test. As you can see, this XLPE material, it elongates quite a lot. This was a few hundred percentages, if I remember correctly. So as you can probably see from these figures, that the cross-sectional area of the sample in the beginning, it's quite different than in the end. So the cross-sectional area changes during the tensile test. So this is why sometimes we want to define the true stress and true strains for the material, and they are shown here. In these definitions, we take into account the actual change of the cross-sectional area and also in the lengthwise. But no worries, generally, we can use these engineering definitions as they are sufficient to describe the performance of the material. It is useful as such and simplified from the realistic scale. But these true definitions also are useful, especially when we are interested in more detailed material behavior. And tomorrow, my colleagues will talk about the modeling, and in the modeling specifically, they would be interested in this true strains and true stresses. So the tensile test data. The measured data, which is the force or the stress and strain, they are plotted in the stress strain curve. And from this figure, we can extract actually quite a lot of interesting information. Firstly, and most importantly, regarding the cable aging, we can extract the elongation break. So this is simply the amount of strain which the sample goes under during the experiment before snapping into half. Then we can extract the tensile strength, the maximum stress here. And then before and after the yield point, we can usually extract some information. For example, before the yield point, we can see for most of the materials, we have this linear elastic region where the material behaves elastically. So from this modulus, we can calculate the yield modulus of the material. And depending on the type of the material, we can see different kind of behavior. For here example, we see the black curve here. We can see how the brittle plastic would behave, or even aged plastic would behave. So basically, we don't have not that much plastic deformation, high stresses when we break down the material. Then we have two types of more typical curves here with tough flats, plastic, and elastomer. We have nicely here shown the elastic region and then the plastic region here. And then we have also how the stress strain curve should look like for rubber material. Here, it's hard to distinguish this elastic regions, how they are shown in this rubbery material. So tensile test and the measured material properties. So here I have gathered some example data from this Team Cables project for crosslink polyethylene material, which has been irradiated with 40 grays per hour. And what we did here, we aged 5 different material conditions, and each material condition had 5 individual samples which were tested. And you can see the dose 2 condition, which has 145 kilogray dose total here, how the individual stress strain curves look like in this case. And as we plot, as we make all the tensile testing for each material condition, we can then plot the results versus the dose observed. And here the first curve here is the elongation break. Then we have the modulus values and also the tensile strength. And as you can probably can see from these different material properties, the elongation of break of the material, there is the largest change in the material property. So the original elongation for an unaged material is about 230%, while it's near zero in the very end of the material. Then we have modulus, which changes also. We have a nice increase. The more we get the dose to the samples, the more increase we can see in the modulus. And then finally, the tensile strength, which is not probably that good aging indicator, as we don't see that much change in the strength properties compared to these other two. So what this figure, it's kind of verifies that the elongation break is currently considered to be the most reliable aging indicator that are used for cable materials, although it's a destructive method. And a common rule of thumb adopted in the industry is that when you have 50% of elongation of break remaining, the material it's still good to be used. So that's kind of this unofficial but official acceptance criteria for elongation of break. So then we move on to hardness measurements. Hardness measurement equipment. This is as a measurement is rather simple. You just apply force on your sample and then you measure the indentation made on the sample. This is also very well standardized method. The short hardness measurements, they cover a broad range of polymers or already A and D. Here you can actually see this short A hardness. The difference between different short hardness measurements is the actual needle shape of the tip of the needle used in the hardness measurement. So in the short D measurement, the needle is just a bit different, and it can be applied for different kind of hardness range of materials than the A hardness. But yeah, so aging effects of hardness are usually the decreased elongation is accompanied by the increase of hardness, and I think this data figure here taken from another project. Here we studied the effects of irradiation on chlorosulfonate polyethylene. This is a lipolon cable that was used in one of the Finnish nuclear power plants, and here you can see as a function of dose, the hardness increases quite nicely. So here we can say that the hardness is sensitive to aging in this sense. And this is the reason why hardness measurement has been applied also in condition monitoring. And in this context, it is referred usually as intender modulus. And in the EIA Tech Doc 1825, you have a quite nice reference data showing how well the indentation modulus works. It has been actually standardized the method, so that already points out that it works reasonably well. And it has been shown that it has good sensitivity and it correlates with elongation break, especially in the very late stage of aging. On the other hand, with this hardness measurement equipment, you have a limited access to the insulator, so that kind of limits the usefulness of these method only for the jacket material. And also some points to be made. The sensitivity of the measurements. It is quite sensitive to the temperature, so it should be quite close, homogeneous temperature where you made the measurements, and when we want to compare it to some other results. Then also when you clamp the hardness indenter around your cable, the clamping itself may affect to the measurement results. So you have to do the clamping also in a standardized way. Then the applied force, the measurement is rather sensitive to that, and also the used indenter tip should be standardized when performing these measurements. Then we move on to ultrasound testing, and here the ultrasound velocity, it depends on Young's modulus, Poisson's ratio, and density according to this equation. So as you probably remember from the previous slides, the Young's modulus changes as a function of aging. So basically this is a measurement of Young's modulus, as we assume that the Poisson's ratio and density remains the same during the aging. And the measurement, it's based on this pulse echo method and thickness measurements. So the ultrasonic signal that is applied on the sample, it will always reflect when it faces an interface. So based on those reflections, you can calculate the travel distance, and when you have the known time for this traveling, you can calculate the sound velocity. And this is the test bench developed here at VTT for ultrasonic measurements of cables. We have integrated the thickness measurement in this test bench. And the current status is that we require sample removal from the cable. So we usually cut about 2 millimeter thick sample from the cable and insert it here between the transducer and perform the measurements. The measurements themselves, they are rather fast, and the data analysis is performed by using MATLAB find peaks function. So it's rather straightforward measurement method, simple and cost effective. Those are benefits of this method. And here you can see some of the results, and we have again measured different samples with different irradiation doses. We have irradiation performed at elevated temperature and then room temperature with various high, medium, and low dose rates. And then we have some unaged samples also measured right here. So I think this is quite good figure, as the trend you can see that the increasing dose causes increase in sound velocity as well. So the method seems to be working. Then, of course, we want to also correlate these ultrasound velocity results with the elongation of break results. So here we can see when we plot the sound velocity versus the elongation break, how the curve changes. So here especially we can see that the ultrasonic velocity changes, especially with low elongation of break values. So its sensitivity kind of improves in the very low end, or when the material is aged quite a lot. Further work requiring for this ultrasonic testing, we still need to improve the scatter and sensitivity of the measurement technique. And then one big challenge regarding these ultrasonic tests is that we need to make it fully non-destructive, so no sample removal from the cables would actually be required. So there's plenty of work still to be done with this method. Then finally, we have the DMA, dynamic mechanical analysis. So DMA measures the mechanical properties of these viscoelastic materials as a function of time. Temperature and frequency are interesting parameters of or how material deforms under these periodic stresses. So generally the measurement can be done in different modes: under shear, tension, bending, or compression. And during a measurement, we can define the class transition temperature, and based on the changes around this temperature point. And this TG, it is influenced by crystallinity, cross-linking, fillers, plasticity, anisotropy, aging, and environmental humidity. And here you can see a typical DMA curve where you have both storage and loss modulus plotted, and then also tan delta. Tan delta can be seen here, and here the tan delta peak is defined as the class transition temperature. Here the challenge is that this method, although useful in other ways, it requires sample removal, and in that sense it is a destructive method. So to summarize the content of the presentation, generally mechanical properties, different kinds of them, can be used as condition monitoring, condition indicator for cables. Here, tensile test, and especially the elongation of break. It's currently the most common aging indicator used, despite it is destructive. Then hardness measurement, it has been shown that it is rather well correlates with aging, and it's standardized and has been used condition monitoring cables. Only one thing is that there are some challenges accessing the insulator. Ultrasound measurement, as I showed you, is possible to correlate with elongation of break. But there is further work required that we can access the cable insulator without any destruction for the sample or sample removal from the cable. Then the DMA, this provides information related to class transition, but its use as an aging indicator is a bit challenging, as this is a destructive method. So this was pretty much my presentation. Do you have any questions?
Thank you, Konsta. So is there any question from the audience? Yes. Yeah, I have a question. Can you hear Sasha?
Yeah, maybe perhaps if you come to the mic.
Yeah, it's this one.
Okay. No.
Yeah, I mean.
Yeah. Okay.
Hello.
Hello.
Yes. Could you please switch to the summary? Okay. So my question here is, you mentioned destructive methods. Can you quantify how much material is necessary for any test?
Any test?
Yes.
Okay.
Yes, for the destructive method. So my question is it possible to remove a small piece from the application, or do you need more material so that has a bigger effect to the installation in the plant?
Yeah. Okay. So this would currently regard tensile test, but in my understanding, the tensile test, you have a specific surveillance samples installed within the containment that you can use and then perform the tensile test. So in that sense, remove the kind of the issue with the destructiveness is like dodged by using these surveillance samples in case of tensile test. And regarding hardness, there will be an issue when you perform the measurement. You will cause or this indentation. How to say? There's a mark of indentation left on the cable, and then I'm not sure how in different countries the safety regulator considers this, whether it's problematic. It is should you provide some kind of taping around the measurement point, or how you should act there. And then regarding ultrasonic measurements, I don't think these haven't been performed as on site yet, at least for my information. But here definitely the goal would be in future that we wouldn't need to do the sample removal because it kind of limits the usefulness of this ultrasonic method to only to the connection points of cables when you can actually remove a really small part of the cable insulator. Then the DMA, I think it's similarly, you can find standardized standards perform this DMA testing, and the sample shape is predetermined. So I'm not 100% sure whether you could manufacture this sample out of a real cable, but here again, you might lean towards using the surveillance samples. I hope this answers to your question at some level.
To the last, it's not clear for me. The DMA test. Can you quantify the
how much
cable is needed or cable insulation is needed?
My colleague Harri would be better to answer this question, but how to say the sample? It's not very large. The actual sample that you put in the. We can prepare those out of those thin sheets. If I had to estimate, it's few millimeters. We'll talk about millimeters.
Okay.
So
it's not that. So it's really not much material you need. So for example, the advantage is you can remove from a junction box, maybe shorten a cable. In general, you have reserved in cable lengths, so it has not a big impact to the application in the plant. So that's exactly was my question.
Yeah.
Okay, thank you.
Thank you. But I think this is a general challenge that where you can make the sampling. So the connection boxes are usually the places where you can the sample for this test. And other, of course, is the surveillance samples.
Okay, thank you, Konsta. Is there any question? See, there's a question from next month.
Do you hear me?
No.
No.
I think it's not connected.
Do you hear me? It's better?
Now it's better, yeah.
Yeah. I have a question concerning the ultrasound measurement. Have you some recommendation concerning the thickness of the sample?
So a recommendation on what?
On the thickness.
Thickness. Yes.
Minimum maximal value that you recommend to use for the technique.
In this Team Cables project, we tried to measure with the 0.5 millimeter tapes, but that was too thin. So 1 millimeter is currently the thickness that we've been performing the measurements.
Okay. And if it's more important, is it a problem for the measurement or not especially?
The thickness.
Yeah.
Yes.
If you have 2, 3, 4 millimeter, I don't know.
Yeah, you should have the sufficient amount of material. Currently, it's 1 millimeter.
Okay.
Okay.
I can answer. It doesn't matter if it's small. It can be like even up to centimeters. That's okay.
Okay.
As long as you know the thickness.
Okay. Concerning the impact of fillers, is it a problem for the measurement or not especially?
For ultrasonic.
Yeah.
Currently, probably Oscar can confirm, but we haven't seen really the effects from fillers. For example, here the data we show was mod 6, and we have quite good correlation, even though this had a quite high amount of the aluminum trihydroxide.
Okay.
But probably we can answer your questions a bit more detail when we finalize the deliverable 5.6. We will have a more measurement data there. Also.
Spoiler alert.
Yes. So stay tuned.
Is there any other question? Yeah, another question from Renaissance.
Yep.
Yes. I have a question concerning the surface of contact for the ultrasound measurement. What is the minimum size of surface contact? Because as you know, cable is round. So for making the measurement, I don't know if it's if you have an idea of the impact of the surface contact with the ultrasound measurement.
Okay, so the current status is, can you see the slide here?
Yeah.
Yep. And you can see the dimensions of this specimen. And you can see the hole in the middle. So the measurements have been performed around this hole. So it's not very large, actually, surface area that is required.
Okay.
And also, if you get a probe with smaller diameter, it becomes less of an issue because the beam is focused on a smaller area. So like in reality, it could be even smaller than that.
Okay. Perfect. Thank you.
Thank you.
Okay. More other questions? Konsta, I have one, but maybe it's a $1 million question.
Okay.
Have you tasted for the indenter modulus? Because as Sasha said, for example, you can do these measurements like in the box, the termination box of the cables. Do you have an idea on how much the indenter modulus would change throughout the cable length? I mean, how much is representative the measurement done in the box rather than the entire cable?
Well, I don't think I'm familiar directly with that topic.
Maybe I can help. Desire. I think it's meaningful to measure at a hotspot. This is the best case.
The harshest condition.
And you have to assure that the junction box is near of the hotspot. Otherwise, it is not representative.
The harshest condition, let's say. And you usually measure that on the sheath, or you go also in the insulation?
No. For insulation. This is a function relevant material of the cover. The sheath is only for mechanical aspects.
So, okay.
But it is, excuse me, it is manageable to remove the sheath for test at a certain position, maybe at a hotspot. Later, you have to fix it. For example, by cutting and make a new connection.
Okay.
So this could be a.
So you create a joint.
Possibility you have.
Okay.
Yes,
That's interesting.
One opportunity. Yes, but you need the aloneness authorities and so on for sure. But otherwise, you will have a big effort of that. If you do it in a hotspot. It's representative for many, maybe thousands other cables. Okay.
I mean, in Team Cables project, we are actually testing this effect along the cable, because we have these cables 30 centimeter, or what was it, 50 centimeter long, and then we peel it down in the middle parts, and then we measure. I think Christoph and Andreas measured with terahertz technique already along the cable length, and we will now measure with Oskari with the ultrasonic measurements. Perhaps we should, just for fun, measure also the hardness and see if we can see any changes in hardness in this length. It really isn't a big deal, so it might be an interesting addition to the project.